Okay, today we're looking at Chebyshev's inequality. I've broken the video down into these parts. The example is coming at the end. I'm going to put the time marker in the description box, so just click on that to jump to whichever section takes your fancy. This is going to be pretty much of an introduction, so I'm not going to do any proofs. You might be happy to hear, or not. As a way to give Chebyshev a good welcome, let's consider this problem. Find the probability that the random variable x is between 2 and 5 when we're told that x is normal distribution. That you can picture, you've done this kind of problem before, that what we're looking for, this is a normal curve, that we're looking at the area between 2 and 5, which you can get this area in various ways. You could do it by direct, for example, by direct integration. However, guys, how about if I just were to tell you this? I want you to find this probability, but I'm not going to tell you that x is normal distribution. But I will tell you two things: that the variance of x and the mean of x, they exist. You may compute them, but I'm not going to tell you them either. Then, what is this probability? Well, in this case, it's similar to kind of problems we've seen before, such as 29 on Bonferroni and 27 on Boole's inequality. Such problems are where you want to find the probability of an event, but you don't have enough information to find it. So then the best thing you can do is to find upper bound or lower bound. So something like, you can say, I don't know exact probability, but I can say that it can't be more than or that it's got to be at least blah 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 number. Okay, Chebyshev is one such result, and here is the theorem. Before we jump into the theorem, I've listed the uses here on this section now. Uses, I'm not going to go into them in detail, so you can just read it here, but for people who are starting out in stats and math stats course, you might be looking for a computer lower and upper bound. That's very popular. You might have to calculate a sample size for a sample mean to achieve a level of probability of at least certain probability. People on the theory side, you can use it to prove the weak law of large numbers, and people who are like doing econometrics, you can use it to prove the consistency of an estimator. Right, so now we're going to turn our heads to the theorem, and this is where we're going to take our time. We're going to break it down into looking at what the inequality says, and then the conditions that the inequality holds. So the theorem is broken into two bits. This is the condition. We'll look at that after we've looked at the inequality. So for k bigger than 0, so k is just a number, bigger than 0, this holds, or equivalently this holds. Right, so they're taking the same information basically. So let's look at this one. X is the random variable, mu is the mean of the random variable, sigma is the standard deviation of the random variable. This says that the distance between a random variable x and a realization of it and the mean being exceeding k times sigma, k standard deviations, is not more than, that's what this says, this number. What this number, 1k squared, is then what we call an upper bound. It's like the ceiling value, because this property cannot exceed this thing here, so we call it an upper bound. Likewise, if we look at this way of writing it, it just says that the difference between the random variable x and its mean, that it's within k times the standard deviation, is at least this number. And so this is what we call the lower bound. This probability must be at least this figure. Let's think of another way to write this inequality. It's a bit of a statement when you're looking at it. It's you know, can't maybe make sense of it when you look at it first time. When you see such things, guys, the tip is drop the probability first and just look at the event. So this is the event. And it involves an absolute sign. Let's have a recap on what absolute means. So absolute value of a less than b is the same as saying that a is between minus b and plus b. So I've taken a figure here, so a is minus 5, then clearly this holds, alright? Two ways to interpret what this inequality actually says. Let's look at this. So if we set a to x minus mu here, just look at that. Okay, and then adding mu to all three terms gives me this. So then the probability of this is the same as probability of this. And how do you interpret this? That this is that probability that this x lies between this value and this value is at least that. Notice if you repeat this, what I've done here, and this time isolate mu in the inequality, so mu then is between this value and this value, it's also at least as big as that. Now interpretation of these two are different. I've interpreted this one already. The second one you actually may well already know. This is a confidence interval. It's the confidence interval for the mean. If we look at the endpoints of the intervals here, they are constants. Mu, sigma, they are population parameters, they're constants in case something you pick. Whereas the endpoints of the interval for a confidence interval is random. Why? Because x is a random variable. So this whole thing is random, that whole thing is random. And that's, you all know that. For if you didn't, now you know. Confidence interval, the endpoints of them are random. So they vary from one sample to another. Now which interpretation we pick depends on, I guess, the question that we're looking at. So some will ask you to find bound of a probability that x is between that, or it might just say find the confidence interval that is at least blah blah. Or should I say, given this, find the probability that confidence interval that it must be at least b. For this one in green, I've just drawn here in blue what we're looking at. So x is between these two values, so somewhere in that interval. Okay, so that's the interval taken. That's this left-hand side taken care of. Almost. Note, guys, one thing. Mu sigma. What are mu sigma? Let's move over here. It's a population mean. It's the expected value of x. Note, it is not the same as x bar. X bar is the sample mean. Likewise, sigma square is the population variance. It's the variance of the random variable. It is not the sample variance. So this theorem doesn't say anything about whether this will hold if you simply replace sigma by s and the mu by x bar. Okay. Now I have, before I made this video, just had a glance of a few videos on YouTube on this, and you gotta be careful when you're watching some of these videos. They have to make a distinction between what kind of mean and variance they're looking at. I kind of feel a bit suspicious when they just talk about means and variances. You've got to be clear. That's why I've got this theorem here, and it's telling you that we're dealing with the mean and the variance of the random variable. So automatically that means, it's the population values, not the sample values. Next, we're looking at the k. The theorem says that k may be any number bigger than 0, but now if you've studied Chebyshev already and you looked in your notes, probably, and on YouTube, probably you'll see them write k is bigger than 1. Now, it's actually true for k bigger than 0. But writing k is bigger than 1 is also true. Now, why would it be that it's true for k bigger than 0, but other people write that it's true for k bigger than 1? It's because it's not all inequalities are useful depending on the value of k you pick. Alright, suppose, guys, we pick k is 1 here. Well, 1 over 1 squared is 1. Well, that's not going to tell me anything useful because I know probability can't be bigger than 1. It's got to be less than or equal to 1. That's something we know for any problem. Likewise, if we set k to 1 here, that's 1 minus 1 is 0. Well, that's useless because we know any probability of any event, it must be at least bigger than or equal to 0. Likewise, if we pick any number from 0 to 1, not inclusive of 0 or 1, then we get, so if we pick a fraction, just think of some number in your head like a half, stick that in, you can see that's bigger than 1. Well, that's true. Probability is going to be less than some number bigger than 1, but it's useless, not informative, is it? And likewise here, stick a half in here, for example. This is then going to be a negative number, and we know probability can't be negative, so this will automatically hold. For that reason, the inequality is useful for k is bigger than 1, and that's what you see people write 1, although strictly speaking it's 0. So let's not draw too much point of that. More importantly is that we actually pick k to be certain numbers like 1, 2, 3. Why? Because then we can say, like if we're looking at this one, that we can say that distance between x and mu is 1, 2, 3 standard deviations from the mean. Of course, we would not pick k as 1 because we just said that's useless. So, or we could, but it wouldn't be meaningful. So usually we say that k is 2, 3, and so on. Some professors like to multiply it by 100 because I've read that on YouTube as well, in your comments on YouTube. That's kind of fine because that means it just turns into a percentage. So it's not exactly a probability, but you can talk about proportion, the percentage of data points lying in an interval must be at least blah blah. Written in this theorem, there are two forms of it, of Chebyshev's inequality, which are equivalent. I'm going to give you another equivalent form, and that's pretty useful, especially from theory points. So this also holds. For epsilon bigger than 0 is less than that. Why is this? What insight does this tell us? Well, it tells us that the upper bound for this probability of this event depends on the size of the variance of the random variable. So think about it. If the variance is small, close to 0, then this is going to be a small number. So the chance of x, this random variable, being far from mu, in terms of exceeding it by this amount, is going to be small. Whereas if this variance was big, it means like x, the distribution is quite spread out around the mean, and so there is a higher chance or high probability that x is far from the mean. So that makes intuitive sense. So I like this one. You can actually get jump between these two and this one just by a suitable substitution for epsilon. But this is not a video of proofs, but you can try it, okay? Now I'm moving to the conditions. Let random variable x, stop right there. Okay, what kind of random variable? Does it tell us like it's continuous or discrete or mixed? No, it doesn't. So it's going to apply for continuous random variables and discrete random variables. Let's continue. Have a probability distribution. Okay, well, it's not told us about a probability distribution, what it must be, but we know that that's not if we were told that, we would be able to calculate the probability exactly, so we're not surprised. Okay, so one thing I would like to attach to what I said about the nature of the random variable, apart from it being applicable for continuous and discrete random variables, is also that about the shape. It doesn't make any mention about, is it unimodal, is it symmetric or not. So it's going to apply for any shape of the distribution so far until we reach the end of the conditions. So in other words, it's going to apply for symmetric as well as skewed distributions, because it doesn't make any mention about the shape of the distribution so far anyway, about which we assume, so further conditions, we assume there is a finite variance, and go sigma square. Okay, finite variance, guys, just means that it's a number, and it's less than infinity. Finite as you'd imagine in your head. That's a very loose way of saying it. And we need a finite mean as well. That's what this says by exists. Now, if you've done some course in math stats, you might not. Oops, I don't want to draw through that. You might not see this condition written in because you don't need it, right? Well, I say you don't need it because it's implied by, as soon as you say it's got a finite variance, it follows automatically it must also have a finite mean. Why? It's proved in my problem 31, guys, if you're interested. Okay, that higher moments imply the existence of lower moments. Some textbooks will state this, but as I said, it doesn't have to be stated if you know that result. So I've now done at least I think I've covered, but you can never be sure. Just talked about the inequality. I just talked you through the conditions. Right, I've got here inequality for the sample mean statement. Okay, let's do that next. A result holds for the sample mean. So there's a Chebyshev for the sample mean, and it's this guy's. Notice, compare it with the result above. It's basically just got an n over here, and you can think about the relationship between the two of them. Again, there's some kind of intuition why this probability here would be smaller than the one for just x above. Why I've given it to you this because often we deal, the sample mean is an important statistic. So clearly, often we want to talk about probability of events that involve the sample mean, even though we don't know the distribution of the sample mean. Okay, next I want to talk about simple calculation. A simple calculation, this tells us in the conditions is that so long as we know there's a finite variance, guys, and a finite mean, we don't need to know their values because we can still compute this. Okay. So for k 2 standard deviations or 3 standard deviations, just substitute k into here, then we've got a bound already for this without knowing what mu is and sigma is, because suppose we pick k is 2, then we'll leave it to just calculate 1 minus that guy. A lot of people do on YouTube, that's a boring calculation, but you get a number for that. And all this says is that without knowing what even the value of mu and sigma is, this says like that the x is within 2 standard deviations of the mean is at least this number. At this point, it's good to bring in the empirical rule. Some people want to know the distinction or what the difference between this empirical rule concerning the normal distribution and Chebyshev's. Alright, well guys, go back to the original problem. Original problem we told x was normal, and then we told you could calculate exact probability. Chebyshev was useful in the case that we didn't know the distribution of x, but we know the existence of mean and the variance. Now, the empirical rule, otherwise known as 68, 95, 99.7 rule, says like, if the random variable we know is normally distributed, then we know that about 68% of the data points lie between 1 standard deviation on either side of the mean, about 95% lie 2 standard deviation mean, 99.7 3 standard deviation mean, and you could get those values by example looking up in the standard normal tables. So these are pretty much exact figures. On the other hand, guys, Chebyshev makes no assumption, remember, in the theorem about the distribution, and so it's not going to be able to say as much, you wouldn't have thought. Indeed, that's true. You're not going to be able to say as much about or with accuracy about these probability of being within these deviations of the mean. So I said for one standard deviation where k is 1, that's not informative because you get 100%, well that tells us nothing. For at least 2 standard deviations, Chebyshev, by substituting k is equal to 2 into the above formula, saying that probability of the sample points being at least 2 standard deviations from the mean is at least 75%. Well, 95% is clearly is contained in this set of at least 75%. So this Chebyshev is true because it contains that, but it's quite vague, you can see, because it's quite far from 95%. 89%, okay, well that's valid as well because that's going to contain 99.7%. The point I'm trying to make here is that these are true, but they could be a bit vague. All right, and the reason that they're a bit vague, or you might say less sharp, is because we make no assumption about the shape of the distribution. This Chebyshev has to apply for symmetric, it has to apply for skewed, bimodal, whatever, so long as the distribution has a finite mean and variance. So it's trying to be something to like a lot of things, so it can't be very good at it. So if it was a symmetric distribution, say it's two standard deviations either side of the mean, that shaded blue has to be, it's going to be at least 75%. This guy here, if we shade it, has to be at least 75%. If we have two standard deviations either side here, it has to be at least 75%. So for all these different shapes, it's got to be at least 75%. So you can see that's why it has to be a bit, it's got to be a bit looser to accommodate all these different distributions. So to sum up, this empirical rule is like giving you pretty much exact values. The Chebyshev is just going to give you just bounds of at least bigger than those figures. Alright, so finally we'll come on to solving a question. Okay, here's a typical question you might see on a course. X is a random variable such that we're told what the mean is of it. Notice under the second moment of it. Use Chebyshev's inequality to determine a lower bound for this probability here. Right, so we want this guy here. If we're going to use Chebyshev's inequality, we need to get it in the form as in Chebyshev's theorem, so that involves the absolute value, doesn't it, of a difference between the mean and the random variable. So a way to proceed, drop the probability, as I said before, make things look a bit simpler first. Just work on the inequality itself, which is like that, guys. Now, first of all, is Chebyshev going to work? Well, first of all, we want to check, because Chebyshev works, guys, for balance between up and down of the mean. All right. That didn't sound like English, but it's late. I'm getting tired. So let's see. Mu is 3. We're looking at interval between -2 and 5. You can see that equidistance is 5 and 5. So it's going to work. If these numbers, that was 5 and that was 10, then that's not going to be balanced around the mean, is what I'm trying to say. Okay, so way to do that to get the inequality of a difference between mean and the mu is subtract mu from each component, which is 3, we're told. So I've done that in purple. Now that is -5 and that is +5. Great, those two numbers match, but it's just a different sign. So that's the same as saying the absolute value of x minus mu, which is 3, is less than 5. We want the probability of this guy, which is the same as probability of this guy, and now we can just plug it into Chebyshev. So here we go. We still need, though, to find the right hand side k. Okay. Let's look at this thing here and compare it to the theorem. It says that this theorem says that k standard deviations is equal to 5. We need to find k, but we don't know what sigma is. However, guys, we're told what the second moment is. It's 13. And we know that the variance of a random variable, the variance of x, is equal to second moment minus mu squared. Substitute the numbers in, we get 4. So sigma squared is equal to 4. Standard deviation is the positive square root of the variance, so that gives me 2. So it's actually 2k is equal to 5, from which you can deduce the rest. Okay. K squared is this guy. Substitute it 1 over that guy's over here. Look, can just do that, but you can follow that for yourself, and it's 0.84. So the probability of the random variable being between -2 and 5 is at least 0.84. And a problem is just like that. Before leaving it, can I just say, before I close down, because notice carefully, guys, this does not talk about x bar, nor is it just simply saying mean, yeah? Although if it said mean, you would know, since it's talking about a random variable, that this mean is this guy here. So we are not talking about x bar. Woof! Right, I think I covered all the points. It's a long video. I'm pretty drained, so I think I've covered it. I think I've covered what I think I want to cover, but always there'll be questions. So was that useful? Let me know.